Hello and welcome to the directions video for the astronomy lab, Motions in the Solar System. Okay, so we're going to jump right into it, taking a look at the handout. Let's first go through all the pages of the handout to show that there's a part one, which is much longer than the other two parts and could have been split into an introduction and a part about Venus because it takes a while till we get there. And so we'll move on to page two and page three with some links and some more images. There's a table to fill out and the first link to a simulator on page four. You can see our questions 7 and 8 on page 5. On page 6, we have another table to fill out and a figure to refer to. On page 7, we have a figure. And on page 8, we have a figure that we need to complete, as well as some more questions. And finally, on page 9, we wrap it all up with a very short page 3 and one last question that takes the form of a table, which is the case because all the time that you are going to be filling in information is always going to be under the heading question number something. Okay, so let's go back up to the top and take a look at part one. There's some introduction here, and I don't want to repeat all of it. I highly recommend you read it. But I will say, in order to motivate the lab, there is a historical point of interest that way back in ancient times, over 2,000 years ago, people who paid attention to such things were tracking the motion of so-called wandering stars, which we now know to be planets in the solar system. Well, they found that sometimes those planets behaved strangely. In other words, they went backwards instead of forwards. What does that mean exactly? Well, we can check that out with the help of a virtual sky simulator, Stellarium. Now, in order to start that discussion, I actually have a few figures here, some older sketches and more modern sketches, and very ornate older sketches that discuss the concept of the planets. What were they? How do we physically represent them? And as some of these figures, in fact, 2 out of the 3, address, how do we explain that seemingly backwards motion that occasionally happens with these planets? Okay, so with that in mind, we had a lot of people over hundreds of years trying to explain this phenomenon. Now, today, let's first of all put ourselves in their shoes or even the shoes of just a modern observer of the sky by thinking about what does it look like when a planet moves backwards? What does that mean? Okay, and this is called, the technical name for it is apparent retrograde motion. Now, it's also called retrograde motion, but the term apparent there calls emphasis on the idea that it's not really moving backwards. There's no stopping and starting of the planets. As we know from Newtonian mechanics and Kepler's laws, the planets are in stable elliptical orbits that are nearly circular. And there is no drastic accelerations, let alone stopping and starting and turning around of planets. And there's also not strange looping spirals or complexity for complexity's sake. More on that later. Okay, so let's move on to the question that first tells us to use Stellarium. So if you look here on page 3, which I'll make a little bit larger, we have that, well, we have a statement, which I'm actually going to go ahead and read right here. One of the greatest challenges that early models of the solar system faced was explaining something called apparent retrograde motion. In fact, the spirograph-like patterns in figure 1 and the smaller circles called epicycles in figure 2 are both results of either tracking or modeling this complicated behavior of the planets. You will now use Stellarium, okay, which I already have open here, to directly observe apparent retrograde motion for yourself. I'll point out on a technical side of getting this lab to work for you, Stellarium can be run as an application or in the browser as a web-based application. Now, the thing is that the directions only directly apply to the downloadable version, which I have open right here. I say that because the controls are different in the web-based version, and it would take a whole nother set of directions to exactly match that system. So if you are using it on the web, you're going to be up for a little bit more of a challenge because you'll have to essentially translate some of the controls to that different version. In other words, it's easiest to use the downloaded version like I'm running right here. It's not terribly important. Maybe if your version number is different than mine, there won't be big changes between the controls. Okay, So start Stellarium and make sure that the solar system objects and labels and markers are selected in the SSO menu. Leave on settings like show ground and atmosphere visualization. Since we want to match the planetary motion you could actually see as a naked eye observer, right? Really standing on the ground at night and all of that. Change the date and time to June 22nd, 2022 at 3 a.m. This day in June was one in a few, in a few in a row. I thought it was going to say one of a few, but one in a few of a row of rare days. Okay, it only happens every few decades when all the planets were visible in the early morning sky. You could see all the planets at once. Usually, some of the planets are going to be on the far side of the planet from you, so you can't see them in your sky, right? Because in other words, the night sky is facing away from the planets because that that just means that the planets are on the other side of the sun from us, so we can't see them at night, right? Think about orientation. A 3D bird's eye view of looking at the solar system from above the ecliptic plane. So let's then get this first idea up and running by going over to Stellarium and following those steps with the settings. Okay, so let's do that. I have to get my menu. So we got a location menu here. We have the sky and viewing options. That's definitely going to be where we want to go. So you can see that this is where we have sky, SSO as referenced in the actual lab. That's the term I was referring to. And here we're going to confirm that solar system objects is turned on. And other than that, I think with those labels and markers, show them, yep, labels and markers, yep. So there we go. So you can see that I want to make sure this is on. This will, for example, put up a label that says Saturn on Saturn. So we definitely want to have that. And by default, it should be. And then the other options I was referring to with the show ground and atmospheric visualization, we can see that atmospheric visualization is by default on. So since it's showing the current time based on my computer time, it's daytime, as you can probably see from the sunlight behind me. So that means that the atmosphere made it, we couldn't see the stars, but of course, if you turn it off, then it's like there's no atmosphere and we could see the stars, okay? So that's the idea. We could still see the sun, by the way, without the atmosphere. It would just be a single bright dot and you could always see the stars because it's all about the scattering of the light that makes it so that we can't see stars during the day. That's not, exclusive. A lot of planets that don't have atmospheres or moons in our solar system could see our sun perfectly fine during their day. They could see stars during their day. So the sun would just be a particularly bright spot that would wash out things immediately next to it. But it wouldn't have the same effect that, well, atmospheric scattering does. Anyway, that's a little bit of a tangent. Let's take a look then. Show ground, that's obviously on. And as far as ground, you can see that it shows up under the landscape tab over here. So we have show ground, show fog. That's not important one way or another, but we'll leave it on. Okay, so then we can go ahead and close this menu. You just go back over to the pop-up over here on the app. So you just move over. You can see so that it had disappeared for a while, and then I can just click on it to turn it off. You can also see I accidentally clicked on a star, and it popped up with all the information about that star. I'm just going to try to click somewhere where there isn't one, which is sometimes a good way to move away from it. And now let's set our date and time. So we're going to do that. I was thinking we could do it maybe down in this menu, but the best way I remember is actually right here. So this is our date and time menu, and this is actually the one I'm referring to. So let's go right to it. Date and time window, which apparently you can also hit F5. Okay, so we need to change the date to 2022. All right, I just double clicked on it, by the way, and then typed in the numbers. You can also just mouse through it, or click on it individually. You can't use the arrows, at least not on my keyboard, to move back and forth between the categories of day of the month, date or year, and month itself. Nor can you move between hour, minute, and seconds with the arrows. But you can use tab if you want to just use your keyboard. So you can just tab through them. So this is me hitting tab all the way through until it hits the end, and then it will not cycle back through, but you can move through it easily that way. So we want June. So we want the 6th month out of the year here. All right, so 6, okay, and then 2022, June 22nd, so 22. All right, and then as far as the time, I think it was 3 in the morning, if I remember correctly. So yep, 3 a.m. So we'll go ahead and put that in. So the clock is a 24-hour clock, so it's going to be 3. But if it was late at night, say 11 p.m., then it would be 2300. But we want 03, and you can see it's not highlighted anymore, so I'm going to tab back over, and 03, and then 00, and 00. Okay. Now you can see that it's actually doesn't by default pause, so the clock is just going to keep running. I do mention the shortcut key to pause it here. So let's see. So we can, it's actually down here. So visualization, Alt Option, and the or Alt slash Option, depending on the keyboard. Those are going to be the same key, just by different names. But then down here I have the equal sign to if you need to go backwards, then it's Alt dash. Okay, so that's forward in time and back in time. But neither of those is pausing it. I'm drawing a blank on the shortcut key for pausing. Let's see. I think it's maybe it's F7. But if you are like me and you can't quite remember the shortcut key for pausing because you haven't used that particular key for a while, then by the way, I'm trying to click away and not click on a star right now so I can get more usable space back. This doesn't actually prevent me from using the menu, as you can see, but it does obviously get in the way, especially in a small window like this. But I'm having a hard time not clicking on a star, so I guess I'll just have to put up with it. Okay, so over here, this appears to be the time running. I think this will pause it if I hit it. Let's see. Okay, so yep, sure enough, we pause time. It's kind of counterintuitive. It almost looks like that now if I clicked on it, that would be selecting pause, but actually it is paused. It's showing what's currently happening. So before it was telling me that it was running. So you can see now that we're paused permanently, at least until we do otherwise, at 3 a.m., 1 minute and 13 seconds after 3 a.m. in particular. Now that doesn't matter, right? So I know I said to do it exactly at 3 a.m. The fact that I let it run for a minute and we're a minute ahead, not a big deal at all, because we just need to be around this time, certainly before sunrise and around this time to get a good view of the planets. All right. So let's go ahead and sweep through and check out the planets. And, I'll leave some of this discovery up to you, but you can see that sure enough, we've seen a few of them already. Look at those labels. And you can confirm for yourself that all of them are going to be labeled, which means they would all be visible. As far as naked eye observation, Uranus and Neptune are not visible to the naked eye. You need a decent telescope to actually see Neptune, and at least a pair of binoculars to see Uranus as a single dot. Okay, otherwise they're just too faint, and Uranus being just a little bit below what's considered bright enough for naked eye observation. And this is even assuming basically zero light pollution, ideal conditions. Okay, so which is what we're seeing here. Although there are some features that are turned on where it's not like ridiculously ideal, best case scenario in the world, but it's still, this is a very low light pollution night sky that was being simulated here. So then you're going to go ahead and discuss it here, talk about your observations, be as specific as you can. Obviously, if there's something some background information, reference it and help that inform your answer. But otherwise, that's just the getting started idea, and then we're going to go ahead and stay in Stellarium and make a few kind of further additions as we move forward in the lab. So continuing right on with part 1, we're going to now move past introduction and actually look at that retrograde motion. So where were we? All right, so we had just talked about seeing all the planets at once. So now we're going to follow the directions here. Now zoom out much more until the entire sky is visible. Okay, so let's head back over here. So I'm using a two finger swipe. I'm just zooming out that way. You can also use the minus key on your keyboard, I believe. Nope, not at all. Sorry. Obviously, that's going to advance time. I was thinking, oh, right, because here where I refer to doing Option plus, that's a larger advancement of time. Whereas when you just hit plus and minus, let's take a look here. So if I hit plus, it looks like it's going 1 day at a time, okay? And then Option plus is, okay, so now that's Option plus is giving me 1 day at a time as well. So actually, I'm not sure if there's a difference. Let's see. So 23, 24, 25. Okay, it's just the way it advances. So it's doing it maybe in terms of the sidereal day or the solar day, because when you use plus and minus, you can see that the time is exactly the same. So 3:05 in the morning, and I could say, go to the 25th, the 26th, 27th, so on of June, and that time remains exactly the same. Whereas if I hold on Option, then, and I hit Advance by doing Option plus, then we're going to go to the 25th, but look, the time is advanced 1 minute and 13 seconds, and then it goes backwards. So yeah, I think it's definitely, actually it went backwards every time. So it's going to be the difference between a solar day and a sidereal day. That's exactly, and if you want the stars, if you want to return to the same point, so you're looking at the same fixed stars, right? Because the planets are not fixed stars. There are, for the most part, all the stars in the night sky don't move at all over the duration of a year, let alone, a few days. So, or even many years. Like it takes thousands of years for stars to significantly move relative to each other as they swirl around the galaxy and so on. So, with all that in mind, if you're going to be advancing a sidereal day one at a time, then you're going to be looking at the exact same portion of night sky. Whereas if you advance a solar day, you're not. So the default is advance a solar day, but what I tell you to do here is actually advance a sidereal day. So you're still, you're looking at exactly the same point out away from the solar system. It's the same heading. Okay. So with that in mind, let's go back and advance some sidereal days, but we still have some zooming out to do. So I'm just going to continue to zoom out this way. It's, with my my trackpad. I'm sure there are other ways to zoom out, but this way is perfectly functional. So you can see that as I continue to zoom out, and then let's say I want to drag up my field of view so I can see more of the sky here. So I'll actually zoom back in. So let's see. So, all right, there we go. It was just moving, it was responding a little slowly, but let's try that. Okay. There we are. Okay, so I grabbed it and moved myself up, or rather so in that case, I clicked on the screen and then swiped. That way I could actually move through, right? So I have a lot of these features. They take some getting used to, especially ones that involve mousing around. Okay, so, or using the trackpad. I zoomed in too much. There, just about right. Now, that's a weird view, right? Because essentially it's like you could see the whole horizons, but through almost like a tunnel because your field of view is so wide. And that's the end of our view because it's ground all along that dark circle. That actually, that represents the horizons going 360 degrees around. So I think I mentioned that you can feel free to turn off things like the atmosphere. So let's see. So you may want to turn off the atmosphere visualization at this point. Now we want to advance time one sidereal day at a time. We can do this by pressing Alt-Option, Alt/Option, right? Same key by different names, and the equal key simultaneously. If you need to go backwards one sidereal day, you can also do the minus key. Okay. Now, it's the equal key /+, right? So the idea is plus because going forward, and then the dash is the minus. Okay. Advance a few days to answer the question below. So which way do the planets normally move across the sky from day to day? Okay, so let's go ahead and advance a little bit. So keep your eyes on the planets. So this is why we might want to turn off the atmosphere, because we're getting to a point where it's sidereal days are going to be interfering with the sunrise and sunset. So, but regardless, we can see that as we advance one day. Oh, I was hitting Command. No wonder. You're probably wondering what I was doing there. Okay, so let's go back. All right, 253. Okay. So, by the way, if you do want to only advance an hour at a time, then holding the Command button and doing plus and minus is going to advance an hour at a time. Great in general, but I don't think necessary for this particular lab. So now let me actually hold the correct key here, and then I can go forward in time. So what we were seeing there was just the motion of Earth, right, spinning around its own axis, and the planets essentially setting. We were not seeing the motion of the planets relative to Earth, right, as both being orbital bodies. So we were not actually seeing that, but we will now. Okay, so I'm going to go ahead and advance a day at a time. All right. So check it out. So now it's really cool, right? Because everything is remaining fixed, right? Before everything was moving because even those fixed in place stars were setting, right, as the Earth spins. But now we're just returning to the same time in the morning every single day, right? So the background stars are absolutely fixed in place. But look what's not, right? Well, certainly not the moon, right? As it goes through its phases and so on. But look what is, right? Mars is moving, right? Quite rapidly. Okay, we can see. All right. Oh, all right, there's the moon again. Okay. what would you say? What's the general motion? Check out these planets. Venus, right? Look at the way Venus is going day after day after day. Okay? And look at Jupiter. Okay? But what was Jupiter doing? Did you notice that? I'm going a lot of days, I know. And Mars hasn't been visible for a while, but Mars initially was just booking it in one direction. And what is Saturn up to, right? Saturn has just seemingly been sitting there the whole time, right? Oh, do you see the Mercury? You see what it did? It's going one way, then it turned around. Oh, there it goes again. And here's Mars, right? Mars moving across the sky. I think we go back. Now we're going backwards in time. We went all the way to 2024, right? So we went a couple of years. If we go back in time here, let's keep our eyes on Mars, which you see arcing across kind of the upper half of our sky tunnel here. It's crowded in with everything else. Huh? Now Mars took a straight path there. We didn't see Mars doing anything retrograde, apparently retrograde, but that just was by happenstance, just because of the time of the year and because of the visibility of Mars. But we can find the time, I'm sure, where we can see Mars do some retrograde motion over a duration of days. All right. And we sure saw it with a couple other planets there. Okay. Now, that's part of the lab, as I want you to be thinking about what you see and doing that exploration yourself. But all I was doing there, especially for the times where I was running many, many days at a time, was just holding down the keys Option and plus. So I was just advancing many sidereal days in rapid succession and observing the phenomenon. You can go back and forth as much as you want and spend some time, right, getting an idea for those behaviors of the planets, for the patterns that you notice. Because you'll be interesting. You'll be like, wait, did that just happen? Or like, oh, that's something new. Because some of these patterns take a while until you actually see them repeat. Okay, so there's that general question though. Which way do they move? Right. I think you should have an answer to that. So the type of motion you observed is called direct motion. On the other hand, retrograde motion is which we also saw, because I advanced it quite a bit, right? I was getting ahead on some of the ideas we'll see in the next couple questions, is basically motion in the opposite direction, opposite that dominant motion that is the rest of the time, most of the time, okay? So here is the beginning of the entry on retrograde motion from Encyclopedia Britannica. Retrograde motion in astronomy, actual or apparent motion of a body in a direction opposite to that of the direct motions of most members of the solar system or of other astronomical systems with a preferred direction of motion, okay? So what does that mean? It means that basically every large system out there in astronomy, such as our galaxy, certainly our solar system, other galaxies, they have rotation that they acquired when they were formed. Okay, so every system that is constituted or created by a giant amount of gas collapsing in on itself and becoming things like stars and galaxies and planetary systems, they all have a lot of common origin there, right? But on different scales, they all end up with some leftover rotation. And there's going to be one dominant direction, because as things collide, there's going to be that one dominant direction that becomes the only direction, because after every collision, everything's more likely to end up in that one direction that there was just initially more of to begin with, okay? So in the case of our solar system, that is motion in the counterclockwise direction as observed from above the ecliptic plane, which is Earth-centrically set as above our North Pole, right? So if you got to Earth's North Pole, right, which is a physically relevant axis because it is our rotational axis, but then you were to go way up into space, millions of kilometers above Earth, and look back down on the whole solar system, you would see that for the most part, the vast majority of objects in the solar system are all moving in the counterclockwise direction. That's the direct motion direction for our solar system, okay? So anything that moves against it is moving retrograde. And there are some objects that actually move against it because they have unique and dramatic origins that led to them being out of sync with everything else. In enough time, right, if you had our system continue, there are going to be other disruptions to our solar system, such as the rapid expansion of the sun into a red giant. That's going to happen in some 5 billion years. That's going to shake things up and allow some of that retrograde motion to get reset. But for now, there's a couple of cases like Venus essentially being upside down, which is to say it's orbiting around its own axis in a retrograde way. There is a large moon of Neptune that is orbiting retrograde. There are many small moons that order in retrograde motion. So with that in mind, we have this idea that there's some examples out there, but they all are exceptions. They're all particular cases where there was some chain reaction that led to it. But for the most part, and certainly during the early formation of the solar system, when there was so many more collisions because there was so much space that hadn't been cleared, essentially like a snowball rolling down a hill, it's picking up things as it goes. The solar system, as it spun up or spun around and the gas coalesced and condensed under the force of gravity, all those things stuck together and became bigger pieces and cleared the path out. Well, that meant that all those opportunities, all those early cases of retrograde motion, they essentially got taken care of, right? They all smashed into each other and became, direct motion. I think you get the idea. Anyway, that's what the terms mean. So let's continue on with the questions. So question 4, when the planets move in retrograde motion, which way do they move? Okay, so straightforward answer there. Just want to make sure you can clearly, compare the two cases, direct motion and retrograde motion. And of course, and I'm not saying from above the ecliptic plane like I was explaining it before, but from the observer on Earth, right? Like looking up at the night sky. All right. So let's see if this strange motion, maybe not so strange after I explained it, but certainly, right, strange to those ancient astronomers because they're like, what the heck is going on? Not only do these stars wander, which is one thing, right, makes them special, but then on top of that, why do they, wiggle back and forth almost, and especially kind of in a weird way, in a sense that it's not like they spend as much time moving one way as the other. They only occasionally like kind of loop around. Okay, so let's see if this, again, strange motion happens to all the planets. Keep holding down the Alt equals key. Okay, just hold it down and keep it running, and watch each planet travel across the background stars. Let at least 3 years go by. So I covered about 2 of them. Right, and pause or slow down the advancement of time if you catch any of the planets doing anything interesting. I'm really talking about moving backwards, right? But that's the thing. You first notice it, and they're just like, sometimes before they move backwards, they just slow down, okay? Because that's like, because from our perspective, what's happening, right? Is we're catching up with them, or they're catching up with us, and so they're kind of come down to a rest, and then they start going back the other way, okay? So well, actually, from perspective, they're going this way. I kind of give away the other answer, right? But then they kind of go back this way, right? So anyway, not all planets will be available all the time, so just wait for them to come back around. Right? As we saw, right? Mars had to come back around because otherwise we weren't seeing it. We were on opposite sides of the sun. All right. And then wait for them to disappear. And with over that, that streak across the sky, that's what you got to pay attention to. When they're not visible, don't worry about it. After you've watched each object carefully, all right? So, I'm sure you're going to have to go back and forth for a while. Record in table 1 a yes, no on whether you see the object undergo retrograde motion. And if yes, then around what dates did you observe it? Okay. Now, some of them are multiple cases, right? Mercury being an example where it happens a lot. Mercury obviously has such a small orbit, and so we have lots of opportunities for Mercury to catch up with us, right? Orbital period-wise, Mercury has an orbital period of only 60 days. 90. It's actually further down the lab. It is 90 days, not 60 days. 90 Earth days, right? Certainly not 90 of its days. More on that later. So with that in mind, that's like a third of our year, right? Less than a third of our year. So and every single time, right, Mercury's coming around, it gets back to us, right? Not after 90 days, but after 90 and some days, it's caught up with us, right? Because it's completing that full orbit in less time, right? Because they're all circles. So it comes back around and it's going to line back up with us. Okay. And so when it does, then there is this perspective that when we're looking at it, we're going to see it appear to drift backwards. Okay, it's like if you pass a car on the road, right? It appears to be like moving one way, right? And then it's going to appear to be moving the other way after you pass it relative to the background. Okay, right? And you have to be kind of looking just the right way to make sense of that. It's not a perfect analogy, but more distant objects moving back and forth, well, then you can really think about it. Or like race cars like going around a racetrack. Okay, so, right, so you're definitely going to fill in that information. I can help you find one. So let's go back. Mercury would be too easy, so let's do a different one. Especially because I was already kind of keying in on Mars, because I expected to see it within that swipe across the sky, and maybe I just missed it. So how about, we'll just go back a bunch of days. So option minus. And let's advance all the way back through September, August, July, June. This is all of 2023. We're approaching the actual date I'm making this video. All right, going back. All right. And looks like a, yep. And it does look like I turned off the atmosphere because we're not seeing any. I guess I didn't notice. Okay. That's interesting though, because I'm not getting my sidereal days. Oh no, we are getting sidereal days, not solar days. Duh. That's why the time is changing, right? And also that's why our stars are staying fixed. Again, right? I just did, because I mentioned that. Let's quickly show it, right? So if I just hit minus, I'm just gonna hit. I keep calling it minus, but really dash, right? So if I just hit the dash key, right? Then you can see, right? I've gone back. Look at the calendar, right? Now we're on the April 4th, April 3rd, right? April 2nd, all of 2023. And every time I'm going back to the exact time of the day, in this case, 8:15, and that would be AM because it's 24-hour clock. So, but look what's happening, right? All those stars, which are those should be fixed background stars, if we're actually returning to the exact same, positioning relative to them, well, they're not. They're not being fixed. They're not fixed because we're going a solar day. So we're coming back around. So Earth is looking, or this particular location on Earth, or any location for that matter, is looking directly at the sun at the same, same point after one full rotation. But that is longer than a sidereal day because we have to, turn a little bit extra to compensate for the fact that Earth has completed 1/365th of an orbit within that time, right? So it takes a little bit more turn, okay? And so hence the whole idea that the solar day is longer than the sidereal day, and when advancing solar days, the stars don't stay fixed in place. Okay, so that's why we want to do sidereal days because it looks so much prettier, right? They stay fixed in place. You know what is also interesting though is you probably notice that there's these other things that clearly didn't stay fixed in place. Like what about what's that? Lyrids, right? And then there's a few other ones that keep popping up every so often. That's because those are meteor showers. And the meteor showers absolutely move relative to us, right? Within the few days that they were actually passing through them, because a meteor shower, after all, is just the leftover tail of a comet that Earth is passing through. It's just a big, hundreds of thousands of kilometers swath of dust that's left in space, and we just got smashed through it every year. All right, kind of cool idea. Okay, so let's find Mars. I'm sure we've had it a few times. Oh, that. No, that's a moon. Obviously, it's moving that fast. Okay. So I'm going to go all the way back. We're actually in 2021 now, which is fine. It does not matter which way you go. There's nothing sacred or special about the 3 years advanced from 2022. The only reason is that I had you go to that particular date in 2022 was because that was one of those special dates where all the planets are visible, just kind of as a starting off point and as just a point of interest. Okay. Whoops. There we go. Let me get back to. Okay, so here's Mars. No retrograde motion on that part, but let's pull it all the way back to the west. Now going backwards in time, don't get the wrong idea here, right? So going backwards in time doesn't mean that like the planets are going in that direction as their direct motion. Quite the opposite. All right, there it was. Okay, so I'm gonna get further backwards in time so we can get the direct motion demonstrated with Mars here. All right, good enough. Okay, so here's an example of finding a range of dates, all right? So I went backwards in time, not a big deal. And I'm starting off by observing Mars here in May of 2020, okay? And I'm gonna go ahead and hold Option and hit the equal or plus sign and start advancing some days. I'm just holding it down. Now pay attention to Mars. I'll probably let off the key and slow down when I start to see. Okay, so now I'm hitting it a little bit more incrementally. So look what's happening, right? Mars is moving steadily towards the east each day, but then look, it stopped. Okay, so that's if you watch, now it's clearly going towards the west, even though we're moving forward in time. This is retrograde motion, clean-cut retrograde motion right there. Mars, between days is drifting backwards, and that's what the astronomers were curious about, right? Because that is like a drift the wrong way, because otherwise every consecutive night it's further towards the east, except for that period where it does the opposite, right? Over just a few days. So let's go ahead and I'm gonna go backwards again, so because I want to find the beginning of it. Now it looks like it's direct motion. That's just because I'm going backwards in time. You can see that the dates. So it says catch like the first date where it began. Okay, so approximately, you don't have to get this perfect, but I'm just looking for it slowing down. Now I might want to turn off the labels for the meteor showers. They certainly are getting in the way. There's a lot of them, so that might be a good option. But right now it's good enough, and we can see it right there behind the northern aquarids. There are all the meteor showers have that ending like rids or ids actually. Okay, so we'll say that is our start date right there. It's really stopped now. Okay, actually I think it already started moving backwards. Okay, so I would put down kind of the beginning of my date range as August 31st. Okay, so I'd write 2020 August 31st as kind of one end of it, and then dash, and then I just wait until it ended. So okay, so we're gonna get the whole period of it drifting backwards, drifting, coming to a stop. See, so now it's it's kind of basically started back going the direct way again. By now it clearly is. So I'd say kind of right there where it's like it's barely moving at all would be the end of it. Okay, because that's the whole idea. It has to come to a rest, right? Apparently, and then start going back the other way. And so the end of this period of apparent retrograde motion of Mars, and this is apparent, there's no real retrograde motion of planets relative to planets. All the planets, every one of them, orbit the sun in the direct way, right? So I mentioned Venus being an exception, but that's its own orbital axis, not its rotational axis. Or, excuse me, it's its own rotational axis, not its orbital axis. Okay, so end of the period is going to be the 16th of November. Okay, so 16th of November would be the end. The beginning date, I believe I said the 31st of August. So there you have it. That is a period, a date range for Mars, and you want to find similar date ranges for all the other planets that you can find it for. Okay, and I'll leave it up to you to determine if it is all of them or not. Maybe you can reason that out. Okay, so continuing on with part one. Okay, so we've established that you can see apparent retrograde motion. You can't miss it if you're paying attention to the stars, okay? And ancient peoples probably paid a lot more attention to the stars because they didn't have city lights to create light pollution, So, kind of something to think about. So now that we have some experience observing the retrograde motion for ourselves, let's return to the Ptolemaic model of the Middle Ages. We're returning to it because it was mentioned in the introduction, and it relates to some of the things we saw in those early figures I asked you to interpret. Okay, which is a totally open-ended answer. I just want you to think about, in fact, it's not even interpreting. You want to write what was the intention of the person that made them. Okay, so to do this, we will use the Ptolemaic model or Ptolemaic system simulator from NAAP Astronomy Labs that can be found here. All right, so if you've been doing a lot of my labs, you probably are already familiar with this website and their simulators. So let's go ahead and head on over. I think I already have it open. Yep. All right. Oh, but I clicked the link, so it's got to reload. And this is the way it runs in the browser. It was that ruffle that came up that is or replaces the previous Flash was the tool, but now there are other ways to run it within. I think within like kind of standard HTML5 or something. So it's a more modern way of running the simulators, and it's working out well. But there are a few that I think they haven't ported over yet at the time of making this video. But all of that aside, let's look at all these cool options we got here. We have an orbit view, okay? This shows all the constellations. And you may think, oh, this is some sort of weird archaic thing. And I mean, it is in a sense, but these really are in space, right? So as Earth orbits the sun, these are groupings of stars and they're located at those points. So, if it's the time of the year that's associated with that zodiac, and the constellation of the zodiac, because these aren't just any constellations, these are zodiac constellations, then that constellation is behind the sun relative to Earth. That's how they were named. That's kind of how it works. All right. So with that in mind, we've got some planetary parameters that we can put. Okay. So as I said, we've got some presets that we can work with. We've got some slider bars here, lots of information. You can get an idea for what they do, right? Look, we're making the size of the epicycle essentially its radius changed. What the heck is an epicycle? It's not a real thing, okay? But it was the model that was proposed for hundreds of years and accepted, right? And that's true of science today. We propose a model, we test its its viability, its simplicity, and then we always are willing to disprove it if new information comes up. Okay, that's the idea of a theory or a model, very closely related ideas. Well, this one turned out to be wrong. Okay, also it didn't really follow best practices in terms of having the simplest explanation, because it's much simpler to just say that Earth orbits the sun. But to be fair, if you just write off a bunch of early astronomers and scientists and say that they never accepted the idea that Earth orbited the sun because religion was getting in the way, that's not the whole story. There were some serious reservations about saying that Earth orbited the sun, because that means that we have to be moving at thousands of miles an hour, right? Whipping through space. Well, that's a weird idea, right? Really, we don't notice that we're moving thousands of miles per hour, a speed that no one had ever, got close to. If you think about how, the rates at which people walk and run and horses move and boats and all that, I mean, we're talking tens, hundreds of times faster than that. So yeah, it's strange to wrap your head around even today, when we know that people can travel at great speeds and go into space. It's still strange, right? Our planet is spinning. If you're at the equator, you're moving at hundreds of meters per second, just relative to the center of Earth, but you don't notice that motion. Well, that's because of principles, in particular, of inertia, and that got accepted and proved and thought about, by the time of Galileo and Newton. But really, I mean, that took some great minds and kind of a change in the consciousness of our species to really understand how that all works. So, all right, let's see what we're going to do with this simulator. All right, so we get it all loaded up, and once the simulator is open, set the planetary parameters to Venus. Leave the control and settings at their default settings, right, for Venus. All right, so let's do it. After all, this part one is supposedly all about Venus, although we've been covering much broader topics of retrograde motion in general and so on. Okay, so let's go from Mars to Venus. Hit OK. All right, so you have to hit OK, otherwise it won't change the settings. So here we are. We've got animation rate, show the deferent, which is the basically that's going to be the path that the path that the epicycle follows, okay? And then show the planetary vector. We don't have to, but it's an option you have. You can show the equant vector, okay? Such complicated names for things that turned out to not even be a correct model, but that's perfectly fine. It's fascinating to think about. It's almost like alchemy or something. Show the Earth-Sun line, okay? So you can see there, right? And because notice, right, in this model, very importantly, the sun orbits us, okay? This is a geocentric model. This is not modern astronomy, okay? This is before Copernicus, before the idea that we had a heliocentric solar system. Everything orbits the sun. And now, I mean, that all makes so much sense. The sun is 99% of the matter in the solar system. Everything else just tiny little leftovers. To say that the sun orbits, one little piece of what was left over from its own creation is an absurd idea. But, we've learned a lot since, sometime over 2,000 years ago, which is, when Ptolemy was, coming up with his models and observing the sky and working among a culture of a lot of astronomers that were studying the sky at that time. All right. So then we have the epicycle planet line. So this is a line that's going to connect the planet. This is the planet that appears to orbit us, like in this case, Venus. Of course, Venus does not orbit us. And this is the distance between it, the planet being the little red dot here. I almost said Mars because I saw the red. I don't know if the color changes. They change the planet, does it? No, it's always just stays red. That's why. Okay. And so then that's just going to be the distance between the actual planet and the center of its epicycle. Because the idea here, the weird idea of the Ptolemaic model is the planets, they orbit as they orbit us, right? And to explain, right, this unavoidable, fact that they clearly, appear to drift backwards every so often, to explain it, Ptolemy came up with this idea that they essentially almost were like on like rotating tables or maybe like gears in a machine. And not that machines were common 2,000 years ago, but that's the way I think about it, almost like a bigger gear with smaller gears rotating on top of it. And so as the big gear turns, that smaller gear also turns. And so then relative to the central axis of the big gear, you would see that smaller gear kind of do this weird looping behavior, right? It would make that spirograph-like, path because that's exactly how you make a spirograph, right? Have a something spinning on top of something else that's also spinning. So let's see, I think the next step is to run the animation. So let's take a look at that. So pay attention to the zodiac strip at the bottom of the window and the planet's path. Can you identify when Venus is undergoing retrograde motion? Describe what you see in the simulator that corresponds to retrograde motion of Venus. Okay, so the idea here is I want you to relate what you're seeing in the simulator. Okay, so this archaic, wrong model of how the planets moved relative to us when we were thought to be the center of the solar system. Okay, that's the simulator. How that one part of that model matches the actual observation that we made in, well, another simulator, although we could have made it, right, by going out in the night sky in a place without a lot of light pollution and tracking the planets, okay? So we want to compare, so like observation, think of, what's going on in Stellarium is real observation, just like the kind that Ptolemy could have done over 2,000 years ago to the simulator, okay? Because I want you to match it up. I want you to say when something's happening in the simulator and, what that actually means, what that would look like for an observer. Because that gets you thinking about like how you would take an observation, in this case, just staring up the night sky and tracking things, and then make a model that matches that observation. Because that's exactly what we're seeing. We're seeing a model, okay? And a complicated one, right? A lot of work went into this. It just happened to be wrong. All right, so let's go ahead and run it a little bit. So, and we can slow it down. It doesn't have to run so absurdly fast. Check that out though. See those little spirograph-like things, right? And they're going to be corresponding to different regions in the sky, right? So they fall in front of different zodiacs. So it's not like it always occurs at the same time of year, but it does occur with a regular, repeating process. Right? So I bet you could help figure that out. By the way, the zodiac strip, so I'm talking about down here. See, look. S is the sun, okay? P is the planet. All right, so good. And as far as the rate at which it runs at, I assume there's a way to slow it down or speed it up. There usually is. Oh, no, I'm not seeing anything. Oh, but I won't dig around for right now. The speed was acceptable, just a little bit on the fast side. Okay, so hopefully you'll be able to answer that question just fine. Then, continuing on, we've got question 7. All right, so question 7. Continue watching the simulator or simulation animation of Venus's motion, okay, in the Ptolemy model, and make any changes to the settings that help you answer these questions based on the geocentric model, which is what it is, okay, of the solar system shown. What phases of Venus would an observer be able to see from Earth? Make sure to consider the relative positions of the Sun and Venus throughout Venus's motion. Sketch a full cycle of Venus's phases below. Okay, the tail has split the year of Venus. Oh, I should say the table. I'm like the tail. What? So there's a little typo here. It should say the table has split the year of Venus into 1/8 segments, much like we do with phases of the moon, right? Because with phases of the moon, we've got our, from new moon back to new moon, and between we have new moon, we have a crescent moon, we have first quarter, okay? Then we have a waxing gibbous, then we have a full moon, so that's 5. Then we have a waning gibbous, and then we have a third quarter, okay? And last, and not, I don't know, certainly not least, I don't know if there's a least unless it's the new moon. Then we finally have the waning. The last one was waning, by the way. It was third quarter, and then it was waning gibbous, and then finally we have a waning crescent, and those are all 8 phases of the moon. Okay, so that's what we want to think about with Venus. Now, with the moon, right? It goes all the way from new, right? So no illumination because it's between us and the sun, to full because now we're between it and the sun, so it's fully illuminated. Okay, and we're not blocking the light of the sun except partially during a lunar eclipse, but for the most part, it's going to be above or slightly above or below. And anyway, it's far enough away that we never completely block the light that gets to it. So that's why it's nicely illuminated when it's behind us relative to the sun. Okay, that's a full moon. Now, here's the thing. With the idea that when you see light coming off the moon, you're seeing reflected sunlight. Okay, no exceptions. Same thing with Venus. And Venus actually, with its cloud cover, is quite reflective. So Venus is very bright when it's reflecting a bunch of sunlight. if it's not reflecting light, then it's not bright at all. It doesn't produce its own light, at least not in the visible spectrum. Like a lot of planets, it produces infrared light, but it doesn't produce any visible light. The only major source of visible light in the solar system is the sun. So with that in mind, that's what you're seeing. If you're seeing a bright Venus in the sky, you're seeing reflected sunlight. Okay, true of all the planets that we see in the sky, and they're really bright. They're brighter than the stars. Okay, because they're just so much closer. Even though the stars are so much brighter, they're light years away. So we're talking trillions of kilometers as compared to just a few million kilometers to the planets. Right, billion at the most. Right, Neptune is over 1 billion kilometers away. Okay, so this can be a little tricky, but I want you to do your best to think about what those phases are going to be. You got to think about it carefully, because there is a difference between the phases that would be found, that could be found with this model, and the phases that would and could be found with the heliocentric model. They're not the same set of phases, but it's not a drastic difference. It's not like with the Ptolemaic geocentric model, Earth-centric model, that you see half the phases that you should with the correct heliocentric model. So it's not like a huge difference, but there will be some key missing phases. Okay, just a few out of that 8 or whatever. Okay, so keep that in mind. Pay attention to that key difference, because that was part of one of Galileo's greatest accomplishments within his publication that got him excommunicated, was that he proposed that the data he collected regarding the phases of Venus disproved the Ptolemaic model. Well, to understand why he would say such a thing, you need to understand that there is a way to disprove the Ptolemaic model with observed phases, and there is. Okay, because there's not the same phases with both models. All right. In fact, let's read this paragraph to check out a little bit more about what I mean. So in the year 1610, Galileo Galilei undertook a series of observations of the phases of Venus, which he would later publish. These observations, along with the work of Johannes Kepler and Galileo's own observations of the moons of Jupiter, marked the beginning of the end of the popularity of the geocentric model of the solar system. In the modern world, we know unequivocally that the sun is the center of the solar system, and it is the law of gravity that underpins this entire phenomenon. Below is an image of a page from one of Galileo's notebooks that show the phases of Venus that he observed through his early telescope. Okay, so you can see, right, we're seeing phases, not all of which you would be able to see with the Ptolemaic model. What do you notice about the phases of Venus that Galileo observed? Are they consistent with the phases? There will be an inconsistency, okay, if you correctly filled out the table above, which would be question 7. So are they consistent with the phases that the Ptolemaic geocentric model predicts? Okay, so I'm telling you they're not, but you need to explain why. All right, so then clearly, right, I kind of give it away here, but again, it's your explanation I'll be looking for. Clearly, the geocentric model of the solar system was incorrect. Okay, so that means we're going to move on to think about more modern models. Okay, so I'll skip ahead a little bit here. A new heliocentric model of the solar system would replace the old, and this is the model we still use today. Okay, and obviously it's been highly tested and used to do things like fly spacecraft around gravitational slingshots of planets as they move outside of the solar system. So we've got that model down quite well and been able to put it to good use. So a model that we have confirmed with extensive direct observation. This modern model of the solar system also includes the terminology of inferior and superior planets, but not those terms. But now those terms are in reference to Earth's own orbit around the sun instead of the sun's supposed orbit around Earth. Okay, let me explain what I mean by that. So a lot to unpack in that sentence. So you can see here that if you're paying attention, there was actually an option for showing superior and inferior. Okay. And as far as doing custom planets, it's actually just exactly the matter of moving these bars around. So you can like set any preset, like start with Venus, and then as soon as you change any of these values, such as eccentricity, motion rate, or anything, it's no longer Venus, right? So that's just the starting off point. And then you can actually, let's go to one of the presets, go ahead to Jupiter. Notice that if I hit OK for Jupiter, it changes it to a superior type planet, okay? That's because as a superior planet, that means that it's assumed to be outside of the sun. And that means that its behavior is going to be different All right, so it's going to have different behavior within the Ptolemaic model. In fact, let me run the simulator to remind myself. All right, so we have, let's see, so superior. I'm surprised to see that the sun is actually whiter out. Why is that? Okay, let's go back to Venus real fast. I think I might have, let's see, because in this case, yeah, it's also inside. I think it's just the way that it's just the way that it's visualizing it with here in this, because if you look at a lot of the models that show the Ptolemaic model, there was a grouping of planets, and you had the ones that behaved in a particular way, Mercury and Venus, namely, and then you had the sun, and then past that you had the other planets, Mars, Jupiter, Saturn, and that was about it, because Uranus not being visible with the naked eye wasn't included in the discussion, right? And certainly not Neptune. And so you have it. They didn't discover that until much later. So you have a case where that was the groupings of the planets, those that were interior of the sun and those that were exterior of it. So inferior was inward and superior was outward. In fact, if we scroll up and look at this figure, we should be able to make it out here. Yeah. So if you look, you can see this is based off the Ptolemaic model. We have the Earth. The moon was the first thing that was supposed to orbit the Earth. Then Mercury was the next out orbit that also orbited the Earth. Again, center of the universe, center of the solar system was Earth. Next was Venus, and we actually see the epicycle shown for Venus as well as for Mercury. No epicycle for the moon because it never displays a apparent retrograde motion, so there was no need to put an epicycle on it. So it was the special exception, I guess, in the model. I don't know how they explained that or proposed to. Obviously, neither the sun also did not have a epicycle attached to it because it just continued with no apparent retrograde motion. But then, sure enough, right, Mars is the first inferior planet, or rather, it's the first superior planet, right? Check the terminology there. So I'm mixing it up. Yeah, superior planet because it's beyond the sun. Okay. So you can clearly see that here. The model doesn't show that, and that's just because of the way it wants to have the zodiac strip and display the way the sun's going to look. And so it just puts puts the sun closer to that outer ring, and that's just a key a key aspect of the visualization, not actually reflecting the model. Sorry if that has a kind of confusing detail to things, but hopefully this figure does clear that up, right? So the Ptolemaic model separated planets that were inward or outward from the sun. Now, we still have that idea of planets being, inward or outward, but now it's, relative to our orbit, right? Not the sun's orbit. Because the sun doesn't have an orbit, not within the solar system. Its only orbit is around the center of the galaxy, which takes about 100 million years. Okay, so here we have the sun, right? Fixed within the frame of the solar system. Here we have Earth, which is orbiting around the sun. Here we have a planet like Mercury or Venus that is on an interior orbit. And that type of orbit is called an inferior planet orbit, okay? So any planet that's closer to the sun than us, it's inferior, right? This is not a judgment on the planet. The judgment is that, there's no judgment. These are perfectly fine planets. And we're not saying that, Mars and Jupiter are better planets. It's just the name given to them. So here we have the superior planet orbit. That would be, any planet that's further out from the sun than us. That includes Mars, Jupiter, Saturn, Uranus, and Neptune, okay? Remember, Pluto's not a planet. It's a dwarf planet. And there's a lot of dwarf planets that are further out. All those trans-Neptune objects, okay? So, all dwarf planets that are further out. So that's the terminology. And you're going to talk about what the terms mean, okay? So you want to define the terms. And I think I have a way to explore the topic if you follow this link. Yep. So this is a page. This would be within that same simulation, or kind of within, it's not the same simulation, but if you go to the home page of the labs, because there's a whole bunch of labs, right? So this one is the Solar Systems Model, or Solar System Models lab, first in the list. And every one of the labs, they're quite detailed, right? they have, kind of like a lab handout. They've got information for instructors, the student guide, and then they have main content, which is kind of background reading in convenient, kind of like single page form. And then they will have a number of actual simulators. In this case, we've got two simulators. There is a planetary configuration simulator and the Ptolemy's model simulator, which we've just been using, right? And so when I have you go to this link, you're going to want to go one of those background reading pages that applies to the simulators, okay? So it talks all about elongations and configurations and goes into the details of that, okay? So you can see we got some pictures similar to the one that I have here. And so I just want you to read over this and be able to define what the different terms mean. And you can see that this is actually a running simulation in its own right. I don't think you can manipulate it. Some of these you can. They're actually basic controllable simulators, just not as detailed as their main ones. But yeah, superior conjunction, right? Lots of good examples here. All right. So that's a matter of doing that reading, checking out that page, and filling in the information. Then you're going to label each of the planetary positions shown in the figure. So the positions I'm referring to are all the ones where there is a circle with some amount of it dark and some amount light. Well, it's actually always half and half. And so this is certainly showing phases, because we're seeing that if the dark side of the planet is facing Earth, that would be a time where the planet would be in its new phase. So it would not be illuminated. There'd be no reflected light coming off of it. And so it'd be very difficult to see. It'd be like a subtle outline, if anything. That's also when you would be able to see a transit, which is where a planet passes directly in front of the sun, which doesn't always happen because of the relative tilt of our orbits, which are slight but non-zero. Because we talk about the solar system being a plane, and it is largely planar, but there's about 5 degrees of variation between orbits of any two planets, and so that makes for alignment that isn't always lined up, especially if you're looking at something that is pretty small, because the actual radius of the sun compared to the distance of the sun makes it only cover half a angle in the entire sky. So about half of the entire 180-degree arc of the sky. So half of an angle means you could fit 360 suns, stacked across each other. So it's, although it's bright, it's a fairly small size and coverage of the sky. But every so often we get perfect alignment between Venus and Mercury, and they pass right in front of the sun. And so with a good telescope and the correct lens, like filters, so you don't blind yourself by looking directly at the sun with the telescope, you can actually see the planet pass in front of the sun, that little dot traveling in front of it. All right. So that's that would happen in this orientation, right? That the label or the name for that particular position. I don't want to say them but you can easily find them on that background reading page. So the same thing, you'll use that page to fill in question 10 or questions 9 and 10. Okay. All right. So this is talking more about the phases of Venus. All right, so to conclude your exploration into the phases of Venus as a window into the advancement of astronomy, right? That this big deal that we have a better explanation for apparent retrograde motion, and that's a huge deal, because it was certainly a mystery, and the Ptolemaic model was not a satisfying answer. Okay, so you will match the phases of Venus shown below with the location of Venus relative to Earth and Sun. Draw the letter corresponding to each phase at the appropriate spot on the orbital figure. Okay, so I just have a decent sized orbital figure, because some of these will be more packed in than others, and you've got 11 points, so more than the traditional 8. There's some kind of extra ones in here, which that makes them, you got to kind of position them all in the right spot. But you are going to have a not complete cycle, because there's not one here that shows a full Venus. That's because it's difficult to see the full Venus, because it's going to be just a couple of degrees off of the sun. Good luck not having your image washed out by the light of the sun. So there are not really any that I know of images taken from Earth-based telescopes that show a full Venus. You just can't quite make it out. It's not unachievable, but it'd be a very difficult picture to take. So that's why we're missing that particular part. But otherwise, you're just gonna show those points, fill in pictures. So for example, if you drew a circle right here to represent Earth, or you could put it anywhere, you could put a circle here to represent Earth, then you would want to show the position of Venus that corresponds to any one of these numbered photos. Okay, and you could have Earth move. You don't have to have Earth stay fixed, or you can have Earth stay fixed and then have Venus be the only thing that you're going to draw in different locations. It's up to you how you want to do it. You just have to make sure that each of them correctly matches the phase as shown above. Okay. All right. Oh, never mind. I put Earth. Forgot. So yeah. So Earth right here is fixed in place. So you're just going to be drawing Venus. So you're going to draw 11 Venuses all around the circle. in their correct positions and numbered. Okay, I think you get it. All right. Well, like I said, number one was way long. Parts 2 and 3 are much simpler. They don't require as much use of simulators, let alone using Stellarium. So I'll just quickly go through them. All right, so part 2 is all about the curious day of Mercury. So I'm going to read over this briefly. The planet Mercury revolves around the sun in the same direction as does the Earth. Mercury is in a 3-2 spin orbit resonance. Okay, what the heck does that mean? As it goes around the sun. This means that Mercury makes 3 rotations on its spin axis. That's like its day, right? So it's on its own, rotational axis for every 2 revolutions. That's an orbit, okay? It makes in its orbit around the sun. So revolutions, rotations. It takes, that's actually how the terms work. So rotation is a planet like moving around its own axis. A revolution is a planet moving around, something that's orbiting gravitationally. So there's those words, although you think of them as interchangeable, revolution, rotation, that in astronomy they actually mean different things. Although I and many people, as they write about these phenomenon, try to clearly state that one of them is an orbit and the other is a motion of the planet. So that's why I say rotation around its axis or revolution in its orbit. Okay, and let's see. So therefore, it takes 2/3 of 88 Earth days, which is 58.65 Earth days, for it to rotate once around its own spin axis. So a Mercury day is 58.65 Earth days. That's a Mercury day. Okay. Now, is that a sidereal day or a solar day? Well, that's the question. So for this procedure, we'll simplify things by approximating the orbital period of Mercury as 90 Earth days. Okay, so none of the decimals, right? Just to kind of round up to nice even numbers. And its rotational period is 60 Earth days. So we got this, 60 and 90. That's a great way to have, this 3-to-2 ratio, right? Because 6 to 9, right, reduces to 3 to 2. Great. All right, so below is a figure of the orbit of Mercury about the sun. The image is not to scale, and the ellipticity, never said that out loud, I don't think, of Mercury's orbit is exaggerated, although Mercury does have the most elliptical orbit of any planet in the solar system. Okay, kind of interesting, right? You think maybe the further out planets would, and certainly the dwarf planets have very elliptical orbits, but of the actual major planets, Mercury has the most elliptical by far. Okay, all the others are much closer to circles. So Mercury is shown at its perihelion. That's its point of closest, point. It's its point being closest to the sun. Okay. The orientation is as usual that we are looking at Mercury from a position above the North Pole of Earth, which is above the ecliptic plane. I point that out because that means that since Mercury doesn't orbit the sun in retrograde motion, not real retrograde motion, it's going to have to move in the counterclockwise direction. So if we're going to advance Mercury, then you have to consider because you're going to draw it at different points, kind of like you drew Venus at different points to match its phases. You're going to draw Mercury at different points as it moves around its orbit in the counterclockwise direction. And so if you were to, split this into portions, right, you'd want to think, okay, well, the whole circle represents 90 days. So if I drew a line right down the middle, then we know that Mercury would be at its aphelion, its point furthest from the sun, after half of 90 days, which would be 45 days. Okay, so right here at this point, Mercury has advanced 45 days, and it's halfway through its year. Okay, now what about its day? How much of its day has gone by? Well, its day, which is more accurately 58.65 Earth days, we're assuming is 60 Earth days. So at 45, it's gone 2/3 of a day, right? Because, the things work out pretty nicely here because if we split the year into halves, we get 45, right? Well, if we then split that 45 into thirds, okay? Because so this right here, right, that would be the 45-day mark. Well, then you could going backwards, you'd have the 30-day mark right about here, okay? And then you'd have the 15-day mark here. So you see it would take 15 days to get 1/3 of the way to aphelion, 30 days to get 2/3 of the way to aphelion, and then 45 days to get all the way to aphelion from perihelion, which is half of a year, half of a full orbit. See? Okay. So what we're doing is you should put points that correspond to 15. Right? I almost want to put it like at a quarter and then all the way up, like the split, because we naturally do it with circles. We split them into quarters, right? But here we're not. We're splitting it into sixths, right? So you're going to have one right here, at 15, and then you're going to have one right here. I guess we split it into eights, and here we're splitting into six. So we're going to have one at 15, and then we're going to have one at 30, and then at 45, okay? Then we're going to have one moving forward. We got to think about this. So it's going to be 60. Okay, so 60 is going to be right there, okay? And then 75, and then 90. Okay, so there's going to be nothing right at the top or right at the bottom, because that would be like, you know, a half of a day. That'd be somewhere halfway between, for example, 15 and 30, right? That would be the point that's like right there, and that's not one of our even points. So we don't draw any that are exactly in the middle. Instead, 15, 30, 45, 60 right there, 75 right there, and then back to 90. Okay, so that's a full year of Mercury going around, full orbit. All right, so a line is shown on Mercury. You can see it right there. All right, if an astronaut were standing where the line is drawn, what time of day would she say it was? Okay, noon, sunset, sunrise, midnight, you know? Well, I'm sure you can figure that out. So now draw another circle to indicate the position of Mercury 15 days later. Then at the first circle, okay? So I talked about where you draw that, right? So, you know, think about its portion of the year, right? It's portion of the orbit. All right, label the circle by the title, Earth Day number 15, okay? Straightforward. All right, assuming that our astronaut hasn't moved her base, right? So it's totally, you know, fixed in place, just hanging out there. From her original position, draw the line to indicate her current location, given Mercury's rate of rotation. Okay, and you know that it's the line shows her current location, but even more than that, it's showing like what she sees, right? It's like her line of sight. Okay, all right. So what fraction of an orbit has Mercury completed? And I'm referring to the 15 days. Okay, it's an easy question, I hope. What fraction of a rotation has it completed? Right. That's a day, by the way. Okay, we talked about that. Now, repeat the above process, drawing Mercury and the astronaut's position for 15-day intervals on the figure above, until Mercury has made one complete orbit around the sun. Your completed chart is the answer to this question, okay? So, let's see. And, oh, right. I should say completed figure. The fact I say completed chart, I think, is because I copy-pasted that from other questions where I was having you complete a chart or a table. But here, when I say completed chart, it makes it sound like something's missing, but there's not. It's not. I'm actually referring to the figure, okay? Because this is what you're completing, okay? So filling this in, you'll get credit for it down here for question 14, all right? And what are you filling in? Well, you like it says above, you're drawing in those locations and labeling, you know, how many or you know what fraction of a day they are, and so on. Okay, of a Mercury day, Mercury year. Now, finally, what time of day is it for our astronaut when Mercury has completed one orbit? When we come all the way back around, what do you think? It's going to surprise you a little bit. This makes you really think. How many more orbits would be required in order for her to be back to the time of day she observed when we started? You get that? That's actually asking for a solar day, because it has what I asked you before, is that a sidereal day or a solar day? I was thinking to myself, well, I'm gonna have to tell you that it's a sidereal day, because otherwise it doesn't make sense. Because when we say that Mercury is spinning on its own axis and it takes 60 Earth days to do that, well, that description of Mercury, that's independent of the sun. So that's in the context of sidereal day versus solar day definitions, that would be relative to the fixed background of the stars, right? Getting all the way back around and pointing the same way, because that's what it means to rotate on your own axis, right? That's the dynamics of that spinning, rotating object, that object being a planet. So when we talk about that amount of time, that's a sidereal day. Now, it's definitely not a solar day. You'll quickly realize as you go through and you draw the line of sight of the astronaut and what she sees on those different 15-day intervals, you realize that the sidereal day and the solar day definitely can't be the same. And it's going to turn out that the solar day is much longer than the sidereal day, okay? Now, how much longer is going to be what you need to answer, but it's a lot more dramatic than the case of Earth, where our solar day is only 4 minutes longer than the sidereal day. Well, oh wow, much bigger difference here with Mercury. So then, how long is the sidereal day of Mercury? How long is the solar day? So hopefully you can answer that one by definition. Just talked about it. Right? This one will require the completing of the figure. Even if you already figured it out, you still got to complete the figure. And if you get stuck, I mean, I'm sure you can, look this up online and figure, see some of the other people. I've seen figures myself that other people have created images that explain this phenomenon. Lots of websites explain it, but, give it a try. See if you can, work it out yourself. And then finally, part 3, you can see it's just a half page way down here. All right. So seasons and days on Uranus. So in terms of very interesting days, Venus is also incredibly fascinating, but we've talked so much about Venus, we gotta move on and talk about other things. And so Uranus, as I would say, has the third most interesting, or maybe tied for second, most interesting relationship between its day and its orbit, and that's because Uranus is on its side. So it's not like retrograde like Venus, where it's upside down. So like its day is almost going the wrong way, but instead it's like its pole is facing the sun. Okay, at least sometimes its equator faces the sun. So that's the deal with Uranus. It's a very unusual orientation. It's like it got knocked over. So the reason we have seasons on Earth is that the axis of Earth's spin is tilted 23.5 degrees. That's a pretty significant axial tilt, okay? From its orbit around the sun. The spin axis points towards the sun, towards the same direction as Earth orbits the sun. So it's not like, we're tilted towards the sun, and as we orbit the sun, we're always tilted towards it. No, that tilt stays fixed. So we orbit with that tilt. So like if this is one point, say this is like, the middle of the summer, like July or something, and the northern hemisphere is tilted towards the sun, then when Earth completes half an orbit and we go around to December, right? So we're going to go around to here, right? Which is not the direction of orbit, but I can't, bring my arm around the back of my head. But now we get here, Earth now is still tilted the same way. So all axial tilts are relative to the background stars, right? They're not relative to the sun. And that's just from physics. That's the way that orbits work. The tilt can never be dependent on the sun. There would be no force to do that, because it would have to actually constantly be exerting a torque on the planet to keep it tilted that way, and that'd be impossible. So Newtonian physics disproves that tilts can be always towards the orbiting body, or the body that's being orbited. So the tilt remains fixed. So got tilt this way after half an orbit. Tilt still the same way, so now the northern hemisphere is facing away from the sun. That's the winter in the northern hemisphere. Okay, so that's the idea of axial tilt and how it remains fixed. Okay, so the seasons are exactly reversed for the southern hemisphere. You can think about my hand, right? This would be the winter, right? Our summers are winter because the southern half, the lower half of the planet, the lower half of my hand is tilted away from the sun. So the planet Uranus revolves around the sun in the same direction as does the Earth and all the planets. However, Uranus has its rotational axis, which should be 2 words, by the way, tilted by about 90 degrees, really close to 90 degrees, not exact, but close, with respect to the perpendicular to the ecliptic, okay? So in other words, the elliptic pole. So in other words, i.e., its spin axis lies in the plane of its orbit around the sun, right? So it's like facing the sun. So if you're going to use my hand to represent axial tilt, this would be a planet with no axial tilt, just straight up, see? Just, facing straight up. That planet would just stay untilted after, half a year would just be still straight up, right? It's North Pole pointing up. So, well, Uranus is like this. It's like tipped over, okay? So there it is, right? With it, say, this is its North Pole facing the sun. The sun's my head, by the way. And so then after half a year, now its South Pole exactly faces the sun. Wild, right? It's not like our poles ever face the sun, like getting like bathed in light, but Uranus's poles do. Wow. Crazy axial tilt, right? That means that sometimes like Uranus is like almost like rolling around the sun, because after like half a year, you have a point where, or a quarter of a year, excuse me, where now Uranus is like this, right? And it's spinning. And, so it's like, it's spinning like this, right? Like, relative to the sun, right? At that point, you would have actually just like we have at the not the solstice, but at the time where the length of the day is the same all over the year. I'm trying to blank on the name for some reason. So you have the equinox, excuse me. So at the equinox, at every point on Earth has the same length day. We have 12 hours of light, 12 hours of darkness. Likewise, on Uranus, at the point that is equivalent to our equinox, which is not going to be one of the extremes relative to the tilt, but instead where the tilt is essentially canceled, same thing would happen there. The whole planet would experience the same length day and night. And as far as the length of days and nights on Uranus, they're actually quite quick. So I point out down here. So let's go through and finish reading, and I'll point out that one thing to remember is that unlike Mercury, that has a very long, very slow down rotation, right, relative to its own axis, Uranus is a very fast one, which is true of all the gas giants. They have very fast rotations, which is part and parcel of the fact that they're so massive and there's so much rotational energy and angular momentum that went into creating them. So they're, even despite their large size, their fast rotation is inherent to their existence. Okay. So, and there's maybe some exceptions in other solar systems, but here it seems to be that's always the case. So the planet Uranus revolves around the sun in the same direction as does Earth. Oh yeah, sorry, I read that. So remember that the spin axis of any planet remains fixed in space in the direction it points, just like a spinning top, while the planet revolves around the sun. That's what I was talking about, okay? It's not, yeah, so hopefully you get that idea, right? If not, look it up, ask me, right? But that's the key idea about orbits, okay? Well, as far as orbits and axial tilt go, okay? So it takes Uranus 84 years to complete one revolution in its orbit around the sun, and it takes 17.2 hours. See, I told you I had quick days, right? Its days are shorter than ours, for it to rotate once around its spin axis. Although of course, calling it a day is a bit of a stretch when you have your pole facing, right? Because there's actually going to be no rising or setting of the sun anywhere on that planet, right? For someone directly at the North Pole, they're just going to see the sun remain fixed in place. It doesn't matter that the planet is spinning every 17 hours. And someone that's, say, like at a northern latitude, so above the equator would be the midpoint of my hand. So someone that's at a northern latitude, they can see the sun, but they would just see it take a path that around the horizon. So it would take 17.2 hours to stay at the exact same altitude above the horizon, and then just track all the way around through all the cardinal directions. Okay, and then anyone that's past the equator can't see the sun at all, right? Because they're on the other side of the planet. Okay, that would be during that one particular day. Now the thing is that one particular day, well, it's a huge amount, right? Because it takes 84 years to go all the way around, right? So it spends a lot of time at any given orientation, right? Especially, in Earth time, it's like a human lifetime just to complete 1 year of Uranus, okay? So it really stays, what we would think of as fixed for a long time in each of those orientations, okay? And passes through many of its own rotations within, each approximate orientation. All right, so all of this combines to answer the one question for this part. I really truncated this part, right? Because the lab is running long anyway. And that's question 17. For each of the times listed in the Uranian year, I had to look up what the adjective for Uranus was, but it's a Uranian year. In the table below, describe the path of the sun in the Uranian sky. Okay, so what would someone see, right? What would like I was talking about just now, right? I gave away one of them, right? The idea of the sun tracking around and just being above the horizon, but just moving all the way around through the duration of a day. All right, and so that's the kind of thing you're gonna answer here. You're gonna have 4 points to consider: the North Pole, 45 degrees north latitude, the equator, and the South Pole. Okay, I could have included 45 degrees south latitude, but it just seemed a little repetitive, so I just put these 4 points, kind of one middle point, and then the 3 key points: north, middle, and south. All right, and I said middle twice, right? So one midpoint, as in not at a special point. Okay, the equator is special. All right, so the North Pole of Uranus pointed directly towards the sun, and you'll fill in each of those. 21 years later, right? So think 21 years, that's a quarter of an orbit later. And then 21 years later again, which is 42 years. Well, 42 years is half a year of Uranus. Okay, so that would get you from here, North Pole facing, to South Pole facing. And that's, after that it repeats, but just, in the opposite order. And there you go. That's the unusual relationship between seasons and the year of Uranus. All right, well, that concludes the lab. Lots of interesting ideas here. I hope this video has been helpful and interesting. Thank you so much for watching.